Please bear with me. And we are now live also on YouTube. So, hey everyone, again, welcome to this 44th community call for Starknet. I'm Henry, your host for today, and I'm joined today by Ariel. Ariel.
Hello.
So, Ariel is a PM at StarkWare. You're Mr. Cairo 1, right? I mean,
Very new title, but yes, let's go with it.
nice. So, but today we're not here to talk exactly about Cairo 1. We are here to talk about Sierra. So, to let me give maybe a small introduction. Currently, Starknet is in version 0.11.2. So the major version is
Point
0.11.
one.
Point one, sorry. Well, actually, I just saw that 0.11.2 was released on integration. So, but yeah, okay. But no, you're right. So where the major version is 11, and version 11 arrived in March, it was hailed as, Cairo 1 arrived on Starknet, and it is true. You can now use Cairo 1 on Starknet, but underneath Cairo 1 is a major innovation, which is Sierra. I personally feel like in the way we presented Cairo, we often said, oh, Cairo is going to be so much nicer to use. It's a great language. It's more comfortable and everything. And it is true. It's absolutely true that Cairo 1 is good. But it's a bit like reducing Cairo 1 to its looks. It looks good, but it can do a lot more stuff. And one of the major things that it came with is Sierra. And today we're talking about Sierra, the impact of it on Starknet, and everyone is most welcome to ask their question. So, Ariel, the floor is yours.
Cool. Amazing. Let me open the slides. And you see my screen right now, correct?
Not yet. Now I can.
Okay, great. Yes, so the title is Cairo 1 and Sierra, but we'll mostly talk about Sierra. But since Cairo is always at the very center, we'll also mention Cairo a lot. Okay, let's go. And again, feel free to stop me at any time also with questions from the audience. Um, so a very rough Cairo timeline. Basically, towards the end of 2020, we first released the very first version of the Cairo Zero compiler. Um, Back then, the white paper explaining the Cairo assembly and the Cairo VM was not even published. I'll say a few words about that. So first we had the first release of the compiler, then we had the sort of expository paper of the VM itself. A few months after that, we launched Starknet on mainnet, and then a year and a half later, we had the first release of the Cairo 1 compiler. And a few months after that, it was finally made available on Starknet. So though it was quite a journey between the Cairo assembly and the first Cairo compiler from Cairo 0 to the new Cairo 1 compiler. So I'm going to talk about a bit about what we had initially, what still exists now. Not everything was thrown away with Cairo 1. Actually, a lot of the stuff remained the same, under the hood at least. And yeah, we're going to talk a lot about the new layer that was added with Cairo 1.
I'm gonna
Uh,
just use this opportunity to say, people, if you want to ask questions, you can ask them on Twitter, you can ask them on YouTube, and yeah, basically on YouTube and Twitter, we're looking for them. Please ask any question you have. It's much more fun when people interact and ask us questions.
Definitely. Yes, so what's Cairo? So Cairo is probably the most overloaded word in the ecosystem. It is used for both the underlying VM, the CPU architecture, the high-level language, which is Cairo 0, Cairo 1 is also Cairo assembly is also Cairo. So basically, everything is Cairo. Uh, Actually, Cairo stands for CPU-R, which is basically a CPU architecture that we can make efficient proofs for. So basically, it's an entire CPU architecture. You have the registers, you have the memory model, you have the semantics of instructions, how instructions affect the memory. So that's actually what Cairo is in a very few words. That's the CPU architecture. And part of this is the Cairo assembly, the instructions for this CPU. And above this, you have higher level stuff which compile down to this assembly. So that was Cairo 0, for example,
Funnily
which is,
enough, funnily enough, when we talk with people who are used to zero knowledge or like doing zero knowledge stuff, especially on Ethereum, they think circom in their head, and they think, oh, so you have a toolkit to build my own circuit and my own prover and my own verifier. And one of the major thing to explain them is that no, you don't have to deal with all of this. Cairo is itself a circuit. We abstract away the need to construct your own circuit, to have your own prover, your own verifier. You're just using one circuit, which is the CPU, which allows you to code arbitrary things.
yeah, you're basically, when you're writing a Cairo program, you're basically writing for that CPU, which we can prove executions for. So if we had efficient ways to prove x86 executions, we wouldn't be here, but we don't. So that's where Cairo comes in. Okay, so the good old days, we had Cairo assembly, which again is part of this CPU architecture. These are the instructions. So you had, for example, instructions to put something in memory, whatever, addition. Actually, addition and assignments are the same thing in Cairo assembly, but I won't really go into that. You only had something like 4 different types of instructions, but that's the Cairo assembly. After that, you had a high-level language that compiles down to it, so it can be funny to call Cairo 0 high level, but you could write in it and it didn't feel like you're writing assembly, and people wrote pretty sophisticated things with Cairo 0. So that's a snippet of things we're not likely to see for long anymore. So that's a very nice piece of history here. Um, okay, so what did we want to change in Cairo Zero? Why even looking at other things? So we wanted a more abstract language. We wanted, for example, the memory model to be hidden from the developer, having a way for him to simply use define variables with simple expression and modify them with regular syntax from other language. We wanted higher level constructs like arrays, vectors, the type system, and not have to work directly with pointers. So yeah, the situation was with Cairo 0 was not trivial, but a lot of the community members did fight with it and did prevail and wrote very interesting things. But eventually we wanted to cater to a much larger audience, and not only people who like really seeing what happens with the memory with nearly every instruction that they code. Okay, so that's why we started with the whole Cairo 1 project, and you can see already in the snippet in the left side a lot of things that are completely non-existent with Cairo 0. You see arrays, you see generics, you see types everywhere. For other than fields, you see different size of units, and essentially a completely different world in that regard. Things you don't see in these snippets are a lot of concepts from Rust. You have traits, you have implementations, you have matching. So a completely different world in this regard. But the topic of this talk isn't really Cairo 1 and the benefit it brings, but a safety property that it brings to Starknet via an intermediate layer between Cairo 1 and Cairo assembly. So just to make the picture more clear, the Cairo VM and Cairo assembly over here at the bottom level did not go anywhere. It's pretty much unchanged from the original paper, and all we did was change the high-level language and create an intermediate representation between the high-level language and Cairo assembly. So basically, a user writes Cairo 1, compiles it, gets Sierra, compiles it, gets Cairo assembly. So it's not like we threw the Cairo VM away, actually, we're still using it as is. We just introduced a new intermediate representation and completely rewrote the high-level language.
So we already had a virtual set of instructions, and now we're adding another one in the middle.
I mean, the VM and the assembly are still the same. I don't know if I'd call it a virtual set of instructions, but yes, Sierra also comes with its set of instructions. So yes, I guess you could say that. Okay, so Sierra stands for State Intermediate Representation, and if you take the right letters at the right places, you get Sierra. The representation is not unique, but yeah, we liked the name. Okay, so like I said, you write Cairo 1, you compile, and you submit Sierra code to the network. Actually, the last step in the compilation is done by the Starknet sequencer. I won't go a lot into the structure of Sierra, but you can think of it as a very small core with all the different types of instructions being what we call lead funcs, which are basically logical units. So addition is a lead func, subtraction is a lead func, putting something in a memory is a lead func. And if you look at a Sierra program, you basically see type declaration, function declaration, and a bunch of lead func applications. So you can pretty much think of a Sierra program as a sequence of lead func applications, which I'm going to talk more about them in the talk. And the most important thing is that it compiles down to the same Cairo assembly that we had before. So again, this part is completely unchanged. Okay, so why do we need the Cairo assembly? Why do we need Sierra? Why do we bother with all those different types of representations in languages? Okay, so the most important point about Cairo assembly is that we need it to prove things. That's why it was developed. We need the Cairo VM in order to efficiently prove execution. So I can't prove a sequence of x86 instructions or EVM instructions as easily as I can prove a sequence of Cairo VM instructions. So if I want to prove a computation, I need a way to express it in Cairo assembly. Okay, so if we want to prove things, we're going to need to use the same Cairo assembly as before, or completely rework the proving architecture. But if you want to keep proving what we proved so far, we need Cairo assembly. So that's not going anywhere. Okay, so what properties should these proofs have? Okay, soundness makes a lot of sense, or it should at least. You don't want the prover to be able to prove an execution of program that does not execute correctly. And completeness. Every execution can be proven. And I'm adding something that is only relevant in the context of Starknet, which means that I want reverted computations to also be provable. What do I mean by reverted? Same thing as it means in Ethereum and pretty much every other blockchain. I have transactions that fail throughout the execution. Can happen basically to any reason. Maybe it's out of guess. Maybe he tried to divide by zero. Maybe a user used an assertion which does not hold. And in that case, the transaction stops mid-computation, but fee is still charged. The sequencer still puts this transaction in a block. The Ethereum validators, for example, include those in a block. And if they couldn't include those in a block, it would have been a very difficult problem because it's work that you're doing as the sequencer, as the entity creating the blocks. If you're not being able to include even failed computations, then you're very easily exposed to denial of service because I can simply send a very complex transaction that fails after a huge number of steps on a very simple assertion, and you won't be able to get paid for the work done so far. So I have to be able to somehow prove even failed executions. I need to be able to prove that your transaction executed for such and such steps and reverted at this point. Is
I
this
think
point
what's
clear? Yeah.
it is. I think it's really interesting when you look at the evolution of StarkNet, I mean StarkX, and then StarkNet. How we got to Cairo One, and this exact problem you're describing is the code is not executed in the same environment. With Cairo Zero, we were trying to prove that we were honest operators. So we were assuming the operator wanted to prove that he is honest. Um, but it didn't really take into account the possibility for somebody to execute code for somebody else and then prove that this execution would fail, right? It was not thought in the beginning as it was not thought for an adversarial environment where somebody would send you code that wouldn't execute and you couldn't prove. So it's really interesting to see this paradigm of proving computation evolving to get more robustness, more resilience. Now we're getting to a point where we actually want to prove that your code is not is failing. So I don't know. I think it's really interesting. I don't know if that makes sense, but
I agree, yes, it wasn't a concern initially, but as Starknet evolved and we started thinking about decentralization and potential denial of service on the sequencer, then it became a very big and concrete concern, and one which Cairo Assembly did not have an immediate answer for.
yeah, and it's also an interesting evolution that impacted the way the performances of the Cairo VM. Right before that, we could do away with the performances of the Cairo VM for sequencing, and now we can't. That's a question for a topic for another day. But I find it really interesting to see the stack evolving with, oh, we actually need something else. So it's one of the logical
Yeah,
next steps.
I'll also talk about that. So it's the definition of a great question. We have some slides about it. Okay, any questions from anyone in the audience so far?
Let me check. No, there's people watching, but no questions so far.
Okay, okay, so we're pushing on. Okay, so basically that's the big problem that CI is attempting to tackle, reverted transaction and DOS attacks, and I'll explain what I mean with the unsatisfiable parts. Okay, so let's focus on this library function in Cairo 0, which looks for an element in the array. You don't really have to know the syntax, but it gets a pointer to an array, it gets a key to search, and it should return a pointer to the element if it's there. So you see here an index variable being defined, and then you check that index is within the bounds of the array, but then you see an assertion that the element you're trying to look for is indeed in the index, which is inside the index variable. So you define an index variable, and without putting anything in it, you expect that it would be the index of the element you're looking for. So as a standalone code, it makes no sense. Like I define a variable, and I somehow magically hope that it will contain the index of the element I want to find. But that's where hints came in, which I omitted them from for brevity. So in line 4, basically, since there are no constraints over index within Cairo, you don't see a substitution into index. It basically means that the prover has complete freedom to put whatever it wants in this variable. And this hint basically looked inside the array and found the appropriate index if it existed. So that's work that's being done outside of the context of Cairo before the program is being proven. But once you know what the index should be, you just put here 5, and the code will compile successfully because the assertion in line 8 will just work. And an interesting thing to notice here is that the element, if the element is not in the array, if I called find element with an array and the key which is not present, then nothing will cause this code to execute correctly. This code is unprovable in this case because this assertion induces constraints that will never be satisfied. Nothing that you will substitute into index will cause the constraints induced by line 8 to be satisfied. So maybe a few more words on the Cairo VM and Cairo assembly. Basically, the way that we're proving Cairo executions is that every instruction translates to constraints on the execution trace. And these constraints are either satisfiable or not. And a simple assert instruction with the left-hand side being not equal to the right-hand side means that your constraints are no longer satisfiable.
So with a dummy analogy, if you try to find an element and it doesn't work, then your Cairo CPU will throw a blue screen of death and crash, and there's no way to recover from it.
Exactly. Exactly. The Cairo VM can't proceed after line 8 if the element is not there, and we cannot prove it. Okay, but there is an advantage here that if the element is there, then I only needed a constant number of Cairo instructions to show that the element is there. I don't have to do the entire search within Cairo, so that makes the proof much more efficient. Okay, so that's Cairo 0, and which compiles down to Cairo assembly and had the hint syntax. I want to claim that this code contains a very dangerous weakness. Okay, so if the element is in the array, the prover can easily substitute the correct value for index and create a valid proof. In the happy flow, nothing goes wrong. However, if the element is not in the array, there's nothing we can put in the index variable that will result in the program running successfully. This means that I won't be able to prove it, which means I will never be able to charge money for it. Because if I can't prove the block, I can't get fees for it. Okay, so what's the problem? I have a very simple denial service attack on the sequencer. Just define a very large array and call find element on a key which is not there. Since this transaction is not provable, you will not get compensation for the work that you did up until the point you discover the element is not present. Because again, recall that someone does the work on line 5, which is hidden in the hint. Someone is going to actually look through the array and figure out the element is not there. It's just not happening within Cairo instructions. So the sequencer is expecting some compensation, but if you defined an array of size whatever, 1 million, then, and you figured out that the element is not there, then tough luck, no money for you. You can't prove this transaction, you can't include it in a block, and you can't get paid. Is the attack clear? Any questions?
It is clear. Let me see if there are questions. So Sibarjun is asking, are there any necessities where we would need to prove reverted transactions? I think we discussed these, but what you described is
This
just
is
one example of that.
exactly, that's exactly
Eh,
an example.
yeah. On Ethereum, you're safe from that because as soon as your transaction enters the VM, you can prove that you executed some instruction as a validator, and if the transaction reverse, you can charge for gas. In that case, you can't prove that the transaction is shit. So you can't charge people for it. So this is a big attack vector because then the sequencer has to do a lot of work and it doesn't get compensated for it.
Exactly. Okay, so what are we gonna do about it? This means we can't keep the situation as is. This can't be the way to look inside arrays within Starknet smart contracts. Okay, so basically the question I'm asking is how find element would look like in Sierra. So recall that I said that Sierra program is basically a sequence of what we call libfuncs. Let's say I want to write down a libfunc for find element, and it should compile to Cairo assembly. And so how would I compile it to Cairo assembly? What would the Cairo assembly look like? Because the Cairo assembly generated from this is not good enough. We already discussed it. Okay. So we must be able to handle the key not found case. So in the happy flow, nothing changes. We can still get the appropriate index from a hint and just assert that the given element is in this hinted location. But in the unhappy flow, we must go through the entire array and actually verify that it is not there. So if you go back here, this means that I would have to replace this assertion with something like if else. And in the else clause, I would have to actually go through every member of the array to verify that it is not there. And in that case, actually, instead of failing, returning something like not found or returning 0 or whatever. But I would have to handle this case within the Cairo assembly generated from this instruction. And this is a very crucial point when libfuncs are being added to CR. Let's say we want to add some logic to the language, and whatever we want to add, maybe find element, maybe some hash function. So you could think of, okay, you just have to write some Cairo assembly for it, and then add this to the compiler, add the find element libfunc, and compile it to the Cairo assembly that you want. But this is not good enough because you have to make sure that the associated Cairo assembly is complete in this very precise sense that there is no flow in which I cannot prove it. There are no cases like this one where for some set of parameters the resulting assembly is unprovable. It has to run successfully for every parameter, for every possible input. So the addition of new libfuncs is very sensitive in this regard because it involves the DOS security of Starknet. So
Are libfuncs something that can be formally verified?
for what?
Or formally verified, like is it possible to formally verify?
I think so. I don't know enough about formal verification to know if it's a good candidate, but it sounds like a good candidate from the
Yeah,
limited knowledge that I have. What happens now is basically a manual audit, which did reveal some completeness issues that were fixed. That's why when we add the libfuncs to Starknet, they are not immediately allowed on the actual Starknet. So if you played around with Cairo 1 and the compiler told you something like this libfunc is not included in the allowed libfuncs list, that's exactly about it. This libfunc was not yet audited, so it's not available on the real Starknet, but locally, when you're compiling, you can use the allowed libfuncs flag and allow to use all what we call the experimental libfuncs, the ones that were not yet
funny.
audited.
It's funny you mentioned that because a bunch of people recently have had this exact issue. They were like their code used to compile and be deployable on Starknet, and now it uses a new libfunc or something that is not allowed yet on Starknet, and so they can't deploy it.
Yes, so from in the initial versions, there were some libfuncs that were renamed or changed, and that basically broke this compatibility. We hope that up to bugs, the only change essentially in CI is the addition of new libfuncs. So yeah, but let's say we add the libfunc, then you write Cairo 1 code, you don't write Sierra instructions. And so it can be in a way transparent to you. Like you see a new fancy Cairo 1 syntax, and you try to compile it, and you get this error, and that's because the new fancy syntax relies on libfuncs that are not yet audited. Yep. So if you come across this error, know that this is about this, and these libfuncs are waiting to get audited, and they will eventually be part of the real Starknet. Okay. So there are other benefits we can get from Sierra except security against denial of service. So I'm going to talk about two main things. One is provable gas metering, and the other is different execution environments, which you mentioned in the beginning. So let's start with the provable gas metering. Let's think how gas metering happens in Ethereum. Okay, so I'm assuming that if you go and look at the whatever geth code or any code that executes EVM instructions, you will see something like a loop that runs an instruction, and after every instruction, it updates some gas counter, which lies outside the context of the VM, possibly. You just maintain it, and every instruction, you have a small overhead which has to update this counter. Like if you did a store, then you got to add 20K gas to this counter, or decrease from it, whatever. But there's an overhead for each instruction. And it's not a problem while you don't care about actually proving this. But if your intention is to actually prove that executing your transaction costs 10K gas, then adding an instruction, even if it's just a matter of updating something in memory, adding an instruction on top of every single existing one is a very significant overhead. You essentially double the proof complexity by doing this, which is very not something you want to do. And Sierra gives us a way to sort of overcome it. There is still an overhead, of course, but it is not the overhead of updating a gas counter after every instruction. And I'll talk about it in a bit. The second big thing is separation of the execution environments. So recall that back here, I said that we need CASM to prove things. So the prover has to know how to execute and prove Cairo assembly. No way around it there. But the sequencer that only puts the transactions in a block, has to do it in a very short time span, or in the future we'll do it in a very short time span. There are no constraints on his execution environment. Like maybe it shouldn't run Cairo assembly. Maybe it can somehow translate Cairo assembly into something else. Or maybe since we now have an intermediate representation before Cairo assembly, it can use Sierra directly and not go through this compilation, which is only necessary for proving. So
when you say
also
this
you want to say a few words
compilation, the
about this.
compilation to CASM that is necessary for proving, it's more like in order to prove it, you need to execute the Cairo assembly in a specific context that instantiates the Cairo CPU, right? Which has a big overhead.
Exactly.
Okay.
And I mean, Sierra has libfuncs like add U64. Okay, so add U64 is a native CPU instruction on any architecture, or U32. I don't really need to work with a Cairo VM for that. I have CPUs who know how to add. So why go down to the much more specific representation um, and not use the intermediate representation directly, which is more about the semantics of what you want to do rather than how exactly to use the memory of the Cairo VM to do this operation.
And why couldn't you do this before with Cairo 0? First of
So
all, because fields are weird. And second, because Cairo 0, you can't know in advance whether this will be provable or not. Whereas with Sierra, if you're able to execute Sierra, you know it will be provable. And so the sequencer knows that eventually he will get paid for it, even if he can't generate the proof right now.
I think the reason is slightly different because you could have executed something else, and let's say if it failed, ignore the transaction as it happens today. I think the biggest reason for why it's possible now is that you have an intermediate representation between user code and proven code. Before, the user sent you Cairo assembly. He may have wrote in Cairo 0, but it sent Cairo assembly to the sequencer. The user did not send Sierra. So nothing you could do as the sequencer. You get Cairo assembly, that's where you're at. But now you're getting Sierra.
Oh, okay. So Cairo assembly, you still can't execute it, for example, more efficiently on x86. So when you received it as the sequencer, you had to execute it on the Cairo CPU. Now, if the user sends you Sierra, that one, you don't have to execute it on the virtual Cairo CPU that has a lot of overhead. You can execute it directly on the metal of your machine and use the
Exactly.
like
Exactly.
transistors. Nice.
Exactly.
But I
So
think there's also like my point, maybe it wasn't clear, is also that if you're the sequencer, you need to know whether your transaction will fail or not.
if you're the sequencer, you need to know whether your
No
transaction
way,
failed or not.
but you could
But
still
you
do
do
that with
know it, yeah.
Cairo assembly,
Yeah.
and you could still do that with Sierra. Okay, sorry.
Yeah. The difference is that unlike the Cairo assembly case where you're just said because it failed and you know you can prove it, now you don't care. It's the user's problem, you're getting the fee. And that's a big difference from the sequencer point of view. Okay, so a few words about gas metering. Essentially, there's gas counting that happens at compile time. There's what we call the local gas wallet, and there's a new libfunc, which is designed specifically for updating this counter, which is called withdraw gas. So let's look at how it works in practice. So that's roughly CR instructions. I mean, not this high-level function declaration, but at least here you see a bunch of CR instructions. But let's assume every line here is a CR instruction. And I have two branches, if and then else. And how we handle gas metering, instead of updating the counter after every single instruction, we can, ahead of time, say how much gas is needed. And every instruction can, and this is something that can be checked in compile time, decrease from this counter. So let's say I added a sort of artificial instruction here. It is called withdraw gas, and it requests 30 gas. Okay, and if I'm looking at the if branch, yeah, the first instruction took a step, another step, and eventually I paid whatever, some number of steps, so I end up with 28 steps available. The else branch also has some requirements. I think the number here should be 35. Okay, so the point is that this is a property that I can check at compile time. When I get the Sierra code, I can check, okay, does this function asks enough guess for what's happening inside? Do I have enough guess for the entire if branch and the entire else branch? So I don't know ahead what's going to happen, whether the if is going to run or the else is going to run, but I can statically check that I have enough guess for the worst case. And very roughly what happens is that instead of updating the counter every single step, we update the counter only at branching points. So let's say calling a function or an if-else branch or some loop. But the counter updates itself can look at a block of code statically. Does that make sense?
Yes, I
Maybe.
think it does. I think I understand that instead of having something being executed at each instruction, the compiler will check whether there's an like for each block,
let me give
we'll make sure
a
that we
concrete
are paying enough. Yeah. Okay.
let me try it with a concrete example. So basically, yes, the goal is to reduce the granularity of this counter update. But let's imagine you submitted Sierra to the sequencer, which does not have this line, which does not have withdraw gas 30. The sequencer looks at this function and it sees, okay, but you have an if branch that requires, I don't know, 20 steps. This is checked statically by the compiler. And where is the gas that pays for these 20 steps? You did not withdraw gas. This is a problem. I'm not going to compile this to Cairo assembly. This is something that is checked by the Sierra to CASM compiler. And if the compilation fails, you can submit it. So if you want to trick someone and let's say write withdraw gas 0 here, it won't work because you don't have enough gas to pay for the static instructions. And in case there was some dynamic thing happening, like a loop inside fib, okay, you don't know ahead of time how much gas you need for the entire loop, but you do know how much gas you need for every iteration. So you would see inside the loop body one withdraw gas instruction. So every iteration of the loop will give you an overhead of one counter update.
Okay. I think it makes sense. I guess my question now is, so does this mean that you can't update the price of opcodes or instructions later down the line?
Very good question. So that makes pricing very sensitive because this thing compiles to Cairo assembly. And if I wrote here with draw gas 30, and it was okay because a plus b costs 1, and whatever initializing a constant costs 2, and so on, these numbers now appear in Cairo assembly. Like this number 30, you would find it in the Cairo assembly of the program, which is being proven. So let's say now you want to update, you say, okay, actually doing addition doesn't cost whatever, 5 units. It now costs 10 units. Then there is no immediate way to do it other than recompiling your Sierra. So these are actually being added by the compiler. You as a user, you don't have to, or as the Cairo 1, in the Cairo 1 code, you don't have to manually insert these withdraw gas instruction. The Cairo to Sierra compiler can actually put the appropriate numbers for you. But if the Sierra was maintained and it is kept by the sequencer today, then if we want to increase the price of some libfunc, then what we can do is recompile the Sierra with updated numbers. And then it will look at the code and say, okay, A plus B costs 10 now, I need a different number here.
So what happens if one, so you're saying the sequencer is basically in charge of checking that gas is paid properly?
It's the
The
responsibility
compiler.
of the compiler, yes. Yes. The sequencer
So,
runs the compiler. So.
and is there any way, like, is there any way for the sequencer to use, like, to tweak the compiler so that he accepts like Sierra code with much lower prices that then become a burden? Like, is this an attack vector where one sequencer can say, yeah, I'll actually allow free contract on Starknet, and then you guys deal with it?
Yeah, it's a really good question. And the answer to it is what we internally call full Sierra. Eventually, compilation will be proven It will be part of the Starknet OS. So there is one compiler which is being proven, and you can deviate from it. So if the compiler expects one set of prices, you can just say, as sequencer A, I want different numbers. You can do it because you won't be able to prove the compilation.
Let me prove you that I prove you something provably.
Exactly. So, so then, no, you won't be able to do it. But it is an attack we need to handle because you're right. A malicious sequencer would maybe want to include a contract that does not pay gas. Everything, all the withdrawals here are with zero. So we'll handle it by having to prove the compilation.
Nice. Is there any kind of timeline or rough estimate for that, or is just on the
For
horizon but
proven
too early to say?
compilation, not yet. For actually proving the compilation, not yet. So now you have the Cairo 1 to Sierra compiler written in Rust, and you have the Sierra to Cairo assembly compiler also written in Rust, and one day written in Cairo, maybe in Cairo 1, which will compile to Cairo assembly. And no, I can't give a timeline for that, but it's definitely in the horizon.
Nice.
Okay. Yes, so we have a few minutes left, so which is great. So now I want to say a few words about separating the execution environment for the sequencer. So the idea is don't go between Sierra to Cairo assembly. You're the sequencer. You are not responsible for proving the block which you are now executing. Why care about Cairo assembly? Just run the stuff on your native architecture. Okay. And what's interesting here is in a lot of the instructions, Sierra has information which basically lends itself to optimizations. Let's consider U32 add. That's a libfunc. And if you see this libfunc being used, you have an immediate way to translate it into a native assembly instruction, which is amazing for you as the sequencer. You definitely not want to go down to Cairo assembly just to perform 32 bytes addition.
So that's why we tell to people don't use felt anymore.
Yes, this is one of the reasons. Indeed, it will also help to transition between fields in the future.
Sure.
But yes, this is one of the reasons. And this is actually not sci-fi. This is a project that is now happening by Lambda class. And they already translated many libfuncs to MLIR, which I think stands for multi-level intermediate representation. And this then compiles down to native code. So they were actually able to move from Sierra to native code and run some functions written in pure Cairo much faster compared to the Cairo VM runner. There's still a lot of work to do on that front, but it's definitely not sci-fi, and we expect that in a few months, a small number of months, they will already be able to run
So
interesting Starknet contracts.
the concrete impact of this will be what? Better performances for sequencing?
And also for native testing and locally working with Starknet
Ooh.
contracts. If
Oh,
you're
yeah,
using DevNet, why
nice.
why go through Cairo Assembly? You're doing tests. You don't care about proving unless you're actually working on proving. But if you're a Starknet developer, you really don't need to run Cairo Assembly on your day-to-day.
Nice.
Yep. And very exciting stuff. And so in the future, we can expect a lot of more libfuncs, more Cairo 1 improvements, freedom in the execution environment, also more of the ecosystem transition into Rust, which is apparently already happening. And yeah, you can go to the Cairo book, Cairo docs, to our Discord, start writing, and yeah, join the fun basically. Yeah, so
Very nice.
questions,
Ariel,
thank you.
Thank you a lot for your time. This was really interesting. It's really in depth, but I think it's really interesting for people to understand the rationale between doing all of this and all the doors it opens. I think that Cairo One is one step on the journey of Starknet, but it's a massive one, right? And it's really important for decentralization. Also, I don't think we can really think of decentralization without DOS resistance and censorship resistance.
Exactly.
So it does lay the foundation for having a resilient network, decentralized. That's pretty cool.
Yep.
Let me check. I don't think we've had any questions. I'm pretty sure that in 2 weeks, Elias will pop up in Twitter saying, "Hey, I watched a call with Ariel on Cairo One. Can I ask some questions?" Well, Ariel, where Elias, you should have been there today, but it's fine. We'll answer your question regardless. No, but all right. I don't see many questions. Thank you for answering mine, Ariel. Always a pleasure to have you, and I'll see you soon.
Cool. Expecting questions on Discord and Twitter, everyone.
I'm sorry? Yeah, sure. So please tag Ariel on Twitter at feedthefed, the one and only. All right. So without further ado, thanks everyone. Have a good day.